Thank you for the kind introduction, Micha, and thanks so much for inviting me. It's a great pleasure. So this is a work that I did after moving to Shufe, and all these co-authors are my colleagues. Actually, I hesitated a bit about the topic. So at the end of the talk, you will see that this is a fairly, so technically speaking, this is a fairly simple work. But I think its applications are quite interesting, and for me it's a conceptually interesting and arguably more applicable piece of work. Okay, so the main topic is the intermediary platforms in the ad exchange markets. So so I'm sure most of this audience are familiar with the online advertising market, but just as a quick refresher, the main roles played in this market are the advertisers, aka publishers, and the advertisers, the ad platform, and the publisher. So the basic scenario is a user opens a website or app, which prompts a publisher to signal that there is an advertising opportunity. So such opportunities are sent to the ad platform, and a transaction happens at the ad platform, aka ad exchange. Typically, an auction takes place in the ad exchange, and the opportunity is sold to one of the advertisers. As we all know, this is a huge market and is the pillar. Well, it's probably the pillar of the e-commerce nowadays. But that's a very simplified and some scheme. In reality, the market is much more complicated and involves many more other players. So, for example, there are the DSPs, the so-called DSPs. They are the demand-side platforms. Those are the platforms that stand between the ad exchange and the advertising agency. Typically, each DSP collects, each DSP serves a number of advertisers. They collect their information, sign contracts, and bid on their behalf to the ad exchange. Some other players are data management platforms. These platforms provide third-party data to both the supply side and the demand side. And then on the supply side, there are platforms that play a similar role to the DSPs. They are called the SSPs, the supply side platform. So they collect advertising opportunities from the publishers and take part in the ad exchange. And the data management platforms actually interact with both the DSPs and the SSPs. So this is a slightly fuller picture of the actual market, and we will be focusing on the DSPs in this picture. So as I said, one of the main roles of DSPs is that it does real-time bidding on behalf of the advertisers to the auction taking place at the ad exchange. In fact, typically TSP also interacts with the DMP. So in some sense, it provides a certain collective service to the advertisers. In the real ad market, the advertisers rarely bid directly to the ad exchange. So So the main question we ask in this talk is what mechanism and bidding strategy should be adopted by a profit maximizing DSP? And given the answer to this question, what are the implications for the advertising market? So some of the main results we obtain is first, we give a full characterization of the mechanism and bidding strategy that maximize a DSP's profit. And then we derive a few consequences from this characterization. First, we show that in contrast to the simple direct auction without intermediaries, simple mechanisms are no longer near optimal for a DSP. From the center's point of view, somewhat surprisingly, its revenue is not monotone with respect to the advertiser's values, meaning that if I add an advertiser to the market or replace an advertiser by another one whose value stochastically dominates the old one, the center's revenue may decrease. And also for the market structure, we ask when there are many DSPs and when advertisers join the market, do they tend to join the bigger ones so that the market power concentrates to a few big DSPs, or do the advertisers tend to spread themselves across many DSPs? So we will see that under certain conditions, so the advertisers tend to spread themselves. So we will. This means that if our prediction is correct, we will see many small DSPs rather than big few ones. And then, if time allows, I'm going to talk about a competition complexity result. This takes some time to explain, so I'll wait until the end if I have time. I believe I will have plenty of time, so please interrupt me if anything's unclear. If not, I'm going to talk about the model. So typically, this model is essentially inherited from Feldman, Mirakni, Mutu, and Pai, from an EC 2010 paper. By the way, this Feldman is John Feldman at Google and not Nihal in our audience. Typically there are, we're talking about, let me first talk about just the two-level auctions. The center, the ad exchange, runs an auction among n DSPs. I'm going to use Y and Q to denote the allocation and payment rules for the center's auction. And then a DSP, let's consider a typical DSP, which we term O. The DSP itself also runs an auction among its advertisers. I'm going to use Z and P to denote the allocation and payments rule for this auction. So each advertiser, which I'm going to call a bidder, I, makes a bid BI to the DSP. Let B be the bid vector. Okay, then what happens is that with probability Zi of B, this is the allocation rule of the DSP's auction, the DSP O chooses bidder I as a contingent winner who makes a contingent payment PI of B. Contingent because the DSP cannot guarantee that this winner is going to have the opportunity to advertise because the DSP needs to win in the center's auction. So based on all these bids and the identity of the winning bidder, the DSP submits to the center a bid theta O of BI. So theta O is a function. It maps a bidding vector B and the winning identity I to a bid to the center's auction. So I'm going to use.
Can I interrupt you with a question?
Yes. Oh, yes.
So some fundamental reason why the DSP can submit only one bid?
That's just what happens. In fact, also we're talking about selling. This is real-time bidding for one advertising opportunity.
Okay.
So each platform, each DSP can win at most one opportunity to begin with. So depending on the auction run by the platform, by the time the DSP bids makes the bids, he will know that only one of them is winning. And for example, if the center just runs the second price auction, he knows it's redundant to bid more, make more than one bid.
Yeah, good point. Thanks.
Yeah, thanks for the question. So let theta be, I'm going to use theta to denote the vector of the DSP's bids. So remember, there are n DSPs. Then according to the rule of the center's auction, the DSP O wins with probability YO of theta and pays the center QO of theta. Then now in the advertiser I's perspective, he will win the auction with probability Zi of B times YO of theta. Zi of B for winning the DSP's auction, and then YO of theta for winning the center's auction. Only when both auctions grant him the opportunity does the advertiser eventually have that opportunity. So so this is just a procedural description of what happens in the system. If there's no other question, I'm going to talk about the information structure and the strategic space. Okay, so we're going to assume that each advertiser I has private value VI drawn independently from distribution FI. This is in line with most of the literature. And we also assume that a DSP knows FI for each advertiser I on it. A central, an important assumption, which I'm going to elaborate in the next slide, is that a DSP O knows its expected allocation and payment in the center's auction for bidding theta O. So by the expected allocation, I just mean the usual interim allocation, interim payment, in the usual sense. So the DSP knows the expected value of YO of theta O, theta minus O, and also the expectation of QO of theta O, theta minus O for every theta O. So I'm going to write YO of theta O and QO of theta O for these interim quantities. So let me...
Just a quick question. When you say that he knows the expected allocation, this is like assuming truthful bidding, because or does he know the strategies of the others? Or
he does not need to know the strategies. He just needs to know that when he bids theta O, he has YO of theta O probability of winning, and that he is expected to pay QO of theta O. He does not need to know where, how this came to be, but he needs to know these things in expectation.
Okay, thanks.
Thanks. Yeah, so this is actually a subtle point. So before I delve into it in the next slide, let me first offer some defense for this. The raison d'être of a DSP is that it knows more about the information and knows how to bid on behalf of a bidder. So and because a DSP typically participates in many auctions per day, per hour, even per minute. So we believe it's natural to it's reasonable to assume that it has enough data to have these estimates. but we will see that this is going to be important. Okay, and in fact, just as Moshe asked, we just assume that because the DSP knows this information, it will best respond to the center's auction. So it does not need to know exactly how the other DSPs bids. It just needs to know these expected quantities to be able to best respond to it. And for our characterization, we just assume that the DSP needs to best respond. Okay, so now when I talk about the DSP's design problem, there are actually three things that need to be decided by the DSP. The allocation rule Z, the payment rule P, and the bidding strategy theta O. Once the DSP decides on these rules, we can calculate its expected profit, which is minus QO plus the sum of PI. So minus QO because that's the expected payment he makes to the center, and PI is the payment made by bidder I on this platform. So his profit is just equal to this difference. So far that's the model. Is there any other question? Okay. So yes, as I promised, I will point out a subtle difference between our model and Feldman et al.'s. There are two assumptions that were not even explicitly stated in Feldman et al. And after a careful reading, we found out what led to the difference in the results that we got. So the first is that the first assumption made by Feldman et al. Is that the DSP does not know YO of theta O and QO of theta O. So these are the interim quantities. And the second assumption is that the contingent payment made by the winning advertiser on the DSP must be decided before the center's auction. So because we assume the DSP does not know YO of QO, and then the contingent payment must be decided before the center's auction. Therefore, this contingent payment cannot depend on YO and QO. So this it actually takes some argument, some careful argument, but why is my slide not moving? Wait, it seems my computer died. Can you hear me?
Yes, we can.
Oh, it seems my PowerPoint stopped. I don't know how.
Would you like to stop share and reshare?
I can't even control my mouse. Where is my mouse? Oh, okay, now it's good. Okay, sorry. Okay, yeah, it takes some argument, but it may not come as a surprise that Feldman et al. Managed to show that under these two assumptions that they made, the only incentive-compatible DSP's mechanism is to post a price P and then bid in the center's auction as if it were an ordinary bidder with value P. So essentially, the only viable, the only incentive-compatible mechanism it can run is to post a price P. And if anyone takes the price, the DSP will just bid as if he has value P for winning the center's auction. if you in some sense, it's it almost seems natural that you know, suppose let's even forget about the posting the price P part. It may seem natural that for the DSP, if he charges a contingent payment P from the bidder, it seems to make sense that then he should the DSP should bid as if he has value P for winning the auction, because when he wins the center's auction, he will get a reward of P. That's, you know, that seems a natural argument. You know, what else can it do? It turns out that this this line of argument is not correct. By the way, I'm sorry, I'm saying two things at the same time. So one thing I want to make sure is to make it clear that it's these two assumptions implicit in Feldman et al. That differentiated our work and led to different results. Then I'm starting another thread, which is to explain why it is suboptimal for the DSP to always bid the contingent payment in the center's auction. So let me explain that. Is it clear what I'm explaining? I hope it is somewhat intuitive to seem, you know, it seems intuitive that the DSP should simply bid the contingent payment to the center. I mean, if the center's auction is IC. It turns out not to be the case. Let me give a high-level intuition why this is not the case. First, let's recall that in any IC mechanism, payments are determined by allocations. So payment rules are determined by allocations. So in the DSP's mechanism, when we say the payments are determined by the allocations, what we really mean is the advertiser's payments should be decided by the eventual allocation to the advertiser, not just the Z, but the product of Z and Y. Therefore, it means that the contingent payment PI, in order to be IC, is it's decided by both Z and Y. But Y itself is a function of theta. So if we let the DSP, if we constrain the DSP to always bid theta to bid PI to the theta, we're actually creating a circle among the variables we otherwise have freedom to decide. So creating this circle basically ties the hands of the DSP and leads to suboptimal mechanisms. So as we will see in the next slide, as our characterization shows, it is not optimal for the DSP to bid the contingent payments.
Can I ask a question?
Yes.
So what is the objective of the DSP?
It's the last, oh, sorry. This one. So the profit of the DSP, yeah, is the sum of its advertisers' payments minus the payment made to the center. He's trying to maximize the expected value of this.
Okay, so like bidding the contingent payment wouldn't make this zero? Or
I'm sorry?
Something. So you just explained why the DSP cannot bid the contingent payment, but wouldn't this make this sum zero?
No, it's actually a reasonable strategy, but it's suboptimal.
Okay.
Yeah. For example, in the second price auction, suppose the center runs the second price auction, then this minus QO, this QO is decided by the other people's bids. if you just bid PI, it still gives you some positive quality. Yeah.
Okay.
Yeah.
So you're saying it can be negative.
It shouldn't. I'm sorry.
So bidding the contingent payment can make its total expected utility, as defined here, to be like negative.
It depends on what the center's auction runs.
Yeah. Like in your example.
No, in my example, it will never be negative. If the center's auction is second price auction, and if you bid the payment, the contingent payment,
okay,
then I mean the contingent payment, okay. I guess part of the confusion may be that I'm mixing two usages of the contingent payment. One interpretation is I charge that payment after you are allocated the opportunity, and the other is the expected payment I charge. I think in these slides I somehow mixed the two, so it becomes a little confusing. Okay. I think for this audience, it's almost unnecessary to review Myerson's result, but let me do a very quick review. So just one slide. As we all know, in a single item auction, the optimal BIC mechanism sells to the bidder with the highest virtual value, where the virtual value is the usual, the form of the famous formula. So here in my talk, what I'm going to use is that the expected revenue of the seller in a single item auction is the expected virtual surplus, which means it's the allocation rule times the virtual value. So all our results extend pretty easily to regular and non-regular distributions. So for simplicity, I'm just going to assume distributions are regular, so that I don't always need to talk about ironing. Okay, so our characterization is this. So for any auction format employed by the center, and for any distribution over theta minus O, remember these are the bids from the competing DSPs. So a DSP's profit maximizing mechanism chooses it as its contingent winner the bidder I with the highest non-negative virtual value, phi of VI, and then bids in the center's auction as if it is an ordinary bidder with value phi of VI. So in other words, the contingent allocation rule is the same as in Myerson's auction, and the bidding to the center is just bidding the contingent winner's virtual value. Is there any question about this? Okay. So before I talk about the consequences and the proof,
I actually have a question. So this is independent of the center, the auctions that the center is running?
Exactly.
So no matter which auction the center is running, this is the way that the DSP needs to act, right?
Yes. So no matter what the center's auction is, the DSP should run this Myerson's auction among its bidders. But the bidding strategy will vary according to the center's auction. He will bid in the center's auction as if it is an ordinary bidder with value phi of VI. But if the center's auction is say a first price auction, then this DSP should bid as if he were, a bidder with value VI or VI in a first price auction.
Okay, so this is not the actual bids in the auction, but only,
exactly.
the value that you imagine you have.
Exactly.
I see.
Exactly. Yeah.
Thanks.
Thanks for clarifying this. Actually, this is an important point. So in some sense, this characterization says for a profit maximizing DSP, the two problems are separate, are decoupled. The mechanism design problem and the bidding problem. So when he thinks about mechanism design, it's just an ordinary revenue maximizing auction. And for the bidding question, he just needs to focus on how to bid in the center's auction if it's not truthful. Thanks. If there's no other question, I'm going to talk about a comparison with a literature called double marginalization. This is a term that's more familiar to economists. So a double marginalization studies a two-level monopoly. So it studies the pricing problem when there's a monopolist manufacturer that sells to a monopolist retailer. And then this monopolist retailer in turn sells to the consumers. So there are two levels of pricing problem. The retailer sets a price, according to the demand of the market, and then the manufacturer can reason about the behavior, the pricing behavior of the retailer, and then calculate its own optimal price. So these two pricing problems are, can be done level by level. So and both of them are simple applications of the typical vanilla monopoly pricing problem. Basically, once you know how to price for one monopoly, then it's you just apply that logic to the next level. And Feldman et al. in their subtly different model, they showed that the optimal mechanism are fundamentally different from Myerson's optimal auction. So one conclusion they drew from their study is that auctions are fundamentally different from monopoly pricing problem in this sense that when you have two levels of auctions, you can't apply Myerson's logic level by level to obtain each level's revenue optimal auction. So our characterization, in contrast, restores the simplicity of the double marginalization literature. So because as you can quickly see, once we have our characterization, we know that because of the decoupling behavior of this characterization, we know no matter what the auction is going to be run by the center's auction, the DSP's auctions are decided if they are profit maximizing. Then the center can based on this calculation, the center can itself calculate its own revenue optimizing auction following Myerson's derivations. And if there's another level, one can just repeatedly apply the same logic. So our result basically shows that in this aspect, auctions are not that different from pricing. Yeah.
So for this to work, actually, the auction, the center needs to actually have like complete priors on the advertisers themselves, right?
You mean, okay, so for the center to be able to design the revenue optimizing auction, in some sense that's not necessary. In fact, as long as he knows the distribution of the maximum non-negative virtual value of each DSP, just as in the Myerson's problem, he would, the center would be able to design that auction.
Sure.
But of course, one can argue how easy that is to obtain. But my point here is that theoretically, it's the same problem as as Myerson. Yeah, it's not fundamentally different. Thank you. So okay, so before I give a proof, which is very short, let me tell you a few consequences that I promised. The first is that simple mechanisms are no longer suboptimal, are no longer near optimal. So as we all know, in a single item auction with a single bidder, the optimal price, the optimal thing to do, the revenue optimal mechanism is a posted price. So a DSP. So from our characterization, we give an example where a DSP with even a single advertiser can make unboundedly more profit than using just a posted price.
Who can ask the question?
Yes.
What if all the DSPs have each one has only a single advertiser? Wouldn't it reduce to the standard setting?
No, that's actually an interesting point. So according to our characterization, each DSP will first it will bid the virtual value to the center. That means the bid. Let's assume the center runs a truthful auction. That means that after each DSP, the value is shaded because the virtual value is smaller than or equal to the original value, and also the values that correspond to negative virtual values are not going to be bid at all. So that means actually I have some examples later, but let's say if you have, say, a uniform 0-1 bidder, then if it bids to the DSP, then this DSP's bid to the center will be 0 half of the time, and then uniform 0-1. And then if there's another level, the probability of bidding 0, or which means giving up, is higher and higher if there are more and more intermediaries. So the value is shaded more and more if there are more intermediary levels.
Yeah, but also more than that, the DSP is actually pocketing all the utility, right? Like the advertisers will end up with 0, right?
Yeah, if you have infinitely many levels of intermediaries, yeah.
No, just with one advertiser for DSP and just 2 levels.
Oh, in that case, actually, the center gets all the revenue.
The center.
Because the center will charge a price of 1. The DSP bids 1. So the DSP charges 1 and bids 1, and the center charges 1. So the money goes to the center.
Okay. This is the uniform 0-1.
No, I'm talking. Sorry, I'm talking about the case where the bidder has a deterministic value 1.
Okay, not the uniform. I see.
Yeah. So the behavior varies a lot according to the distribution. Yeah.
But is it true in general that the advertisers will end up with zero utility if there is only one advertiser per DSP? Because essentially the DSP will take all the utility.
Good question. Let me see.
We can take it offline.
I don't know. I don't think that's the case. There is still some information rent, I think. Okay. Think about say for the uniform 0-1 case. So the DSP will bid, you know, 0 with probability half, and then uniform 0-1 with probability half. And therefore the center will set a price of half. That basically means the bidder will win whenever his value is more than 3/4. So he does have a utility of, you know, the utility above 3/4. He does have that utility.
So how much will the DSP make in this example? I'm a bit confused.
Okay. So
like how much the advertisers will actually pay?
What's the setting we are analyzing now?
Okay, so we're analyzing a single bidder, a single DSP, and the center. The bidder's value is uniform between 0 and 1. So the center will bid 0 with probability half, and uniform 0-1 with probability half, and therefore the center will charge a price of half, will post a price of half. So the allocation rule from the bidder, the advertiser's point of view, is 1 if his value is above 3/4, and 0 otherwise. So that is so. And so his utility is, you know, is the utility above the 3/4.
So like the DSP will make 3/4, and he will gain the rest.
Yes, I think so. Yeah.
I see. Okay.
But yeah, it's a bit, you know, difficult to do the calculation on the fly.
Yes.
Yeah, let's continue.
Yeah. Okay. Thanks. No, actually, I don't think the DSP makes that much, because the DSP needs to pay half to the center. So the center makes a revenue of half times 3/4. Sorry, half times a quarter. So the do you see what right? Yeah.
So he will make a quarter times a quarter or something like that.
Yeah, something like that.
Okay.
Yeah. So yeah, it's so in this case the utility is divided among the 3 parties. All of them get something. Okay, so this proposition, let me just skip it. It just says, you know, posting a price can be arbitrarily worse than the optimal mechanism for a DSP. Basically this because for, you know, for certain bidders, you know, the virtual values give the DSP much more control over the whole thing. So, but this already shows that other simple auctions cannot be are out of the question for being near optimal. For example, second price auction with whatever reserve, because for a single bidder, you can't even do a reserve price. So with more bidders, it's even more hopeless for the other simple auctions. I'm also going to state without proof that the center's optimal revenue may decrease when an advertiser's value distribution is replaced by one that stochastically dominates the original one. I think I can show you by an actual example the following consequence, which I find a little amusing. So if there is one level of intermediaries, one can actually show that the center's optimal revenue weekly increases when a new advertiser joins the market. However, if there's more than one level of intermediaries, so there's a DSP bidding to a DSP which bids to the market, then the center's optimal revenue may decrease when a new advertiser joins the market. So here's an example. So if you have one advertiser with deterministic value 1 bidding to the DSP, to a DSP, to another DSP, to the center, then as we analyzed in the previous slide, in this case, all the revenue goes to the center. So the center gets revenue 1. So now suppose another bidder, another advertiser joins the market, and his value is uniform between between 2 and 3. Then the virtual value of this new advertiser is uniform between 1 and 3. And therefore, the value, the bid made by the DSP to the first level DSP is uniform between 1 and 3. The first bidder is basically ignored. Then the virtual value of this distribution is 0 with probability 1/4 and uniform between 0 and 3 with probability 3/4. And therefore, the center's optimal auction is to post a price of 2/3, and he will get a revenue of 2/3 times 3/4, 2/3 times 3/4 times half. Sorry, 3/2 times 3/4 times a half, which is 9/16. And this is smaller than the revenue 1. Okay, and one last consequence that I really like is that, so if we assume the center maximizes its revenue, and the DSPs are profit maximizing, and if we assume all the advertisers' values are RID, then an advertiser with any value V has weekly higher utility when it bids through a DSP with fewer bidders than through a DSP with more bidders. So basically it means, so if we make the RID assumption, then an advertiser always benefits from bidding through a smaller DSP. So this suggests that advertisers tend to spread evenly over the DSPs rather than concentrate to a big one. So in the interest of time, let me just give you a sketch, the proof of the characterization. So let's recall that the characterization says the mechanism design and the bidding should be separated. The mechanism design should always be the Myerson optimal auction, and the bidding should be that the center behaves as if it's a value with equal to the virtual value, equal to the contingent winner's virtual value. Okay, so let's consider any mechanism ZP. Remember, this is the DSP's auction, and a bidding strategy theta O. Together, ZP and theta O, suppose they induce an incentive compatible mechanism for the advertiser. Then by Myerson's characterization, we know that the DSP's profit is, so first let's calculate its revenue from the bidders. It's the virtual value times the actual, times the eventual allocation. So the virtual value is phi I from each I, and the allocation is zi times yo. And then and on behalf of each I, the allocation, the payment made to the center is equal to zi of v times qo. Zi of v, because we are making the payment to the center on behalf of I only if I wins the first auction. So that happens with probability zi of v. And when that happens, we make a payment of qo of theta o. So given this expression, we can extract the term, the factor zi of v. So therefore the profit is equal to sum over I zi of v times phi yo minus qo. Now this is the quantity we would like to maximize. But the nice thing here is that zi here, so zp, so p already disappeared from this calculation. So z now is now separated from theta, because only the big factor in the parentheses has anything to do with theta. Therefore, in order to maximize this quantity, we should maximize for whatever z we decided. We want to maximize this term in the parentheses term by term. And what is this phi times y minus q? Well, this is precisely the utility of a bidder, an ordinary bidder with value phi I of vi, if he bids theta o in the auction yq, because yo of theta o is his allocation and qo of theta o is his payment. So phi I times yo minus qo, that's exactly the utility for bidding theta o of a bidder with value phi I. This already shows that no matter what the mechanism is run by no matter what the z and p is, the DSP should bid in the center as if it were an ordinary bidder with value phi I. Then another easy observation is that in any equilibrium we don't even have to assume equilibrium. As long as the DSP is best responding to the bidder, to the center's auction, its utility is weakly increasing with the value phi I. And therefore, in order to maximize this big product, he should design zi of v to maximize. He should give the allocation, the contingent allocation, to whichever bidder that maximize phi I of vi. And that's exactly Myerson's auction. In conclusion, the DSP should therefore pick the advertiser with the highest non-negative virtual value as the contingent winner. So the proof strategy just expresses the profit separated into two factors. So the ZP and theta are separated, then we see how to maximize the term with theta, and then realize that that term is monotone with theta, with phi, and therefore we should design Z so that the contingent allocation goes to the maximum phi. I'm running out of time, so so maybe let me just do just conclude first. So we give a characterization of the mechanism and bidding strategy that maximize a DSP's profit.
We have a few more minutes if you want just to state the Bülow-Klemperer result, maybe.
Sure.
If you can do it in a few minutes.
Yes, I think 3 minutes suffice. Okay, thanks. So as we all know, Bülow-Klemperer is about comparison between welfare maximizing and revenue maximizing. So therefore, I first need a welfare maximizing mechanism. It's actually not hard to see that if the center runs the second price auction, then the welfare maximizing for DSP is to run a second price auction in turn and bid the winner's value. In this case, the DSP in fact becomes somewhat transparent. In other words, a bidder bidding through a DSP that runs second price auction does not see the difference between that and bidding directly to the center. We will call this auction running second price auction and then bidding the winner's value. This auction we call it BTV, bid the value. So this we will treat it as if will be our welfare maximizing mechanism. And now suppose all advertisers are RID. We're now considering a scenario where a DSP has K advertisers, and then there are N other bidders bidding directly to the center, or equivalently bidding through DSPs that in turn run second price auctions. And we're comparing two things. That if the platform runs, the revenue of the platform running the BTV auction and the revenue of the platform running the optimal auction, the profit maximizing auction. So we denote BTV KN and OPT KN, these two terms, these two revenues. So the competition complexity result we get is that we will need, if we're fixing the number of bidders outside the DSP, then we will need a certain number of bidders on the DSP in order to ensure that running BTV gets no less revenue than running OPT. And this is a by criteria comparison. So if we consider BTV of L, and meaning there are L bidders on the DSP, then if L is greater than or equal to essentially square root of Kn plus K, then the DSP's revenue is no less than running the profit maximizing auction with K advertisers.
And who do you also have a lower bound for this?
Yes, there is a lower bound, but this is essentially tight.
This is tight. Great. Okay, thanks.
Yeah. Thanks for asking. And this does not assume regularity. Thanks. So let me just, or maybe I should leave this on the screen, and I'm happy to take questions.